This is 1984 Colorado Math Olympiad. Problem number 5. 41 rooks are placed on a 10 by 10 chessboard. Prove that you can choose 5 of them that do not attack each other. We say that 2 rooks attack each other if they are in the same row or in the same column. Let's divide our 10 by 10 board into 4 smaller boards, 5 by 5 each. And let's group these 4 smaller boards into 2 sections diagonally. They are shown on the diagram as section 1 and section 2. Since the total number of rooks is odd, one of them has more rooks than the other. Let's assume, without loss of generality, that section 1 has more rooks than section 2. Then the maximum number of rooks in section 1 is 41, and the minimal number of rooks is 21. And let's make the rule that we'll select our 5 rooks that don't attack each other only from section 1. If we succeed in doing this, even with a minimal number of rooks equal to 21, then we're done. Obviously, if number of rooks in section 1 is more than 21, then this selection will be also possible. The diagram shows an example of 5 rooks selected from 21 rooks placed in one 5 by 5 board so that they don't attack each other. We will prove that such selection is always possible in this situation. We will also prove that 2 rooks that don't attack each other can always be selected if the number of rooks placed in a 5 by 5 board is not less than 6. Then 3 rooks can be selected if at least 11 rooks are placed in such board. And finally, 4 rooks can be selected if at least 16 rooks are placed in such board. These intervals cover the entire number of rooks from 1 to 21 rooks, divided in the ranges 1 through 5, 6 through 10, 11 through 15, 16 through 20, and then exactly 21 rooks. The proof of the first 2 cases is trivial. Of course, 1 rook can always be selected if the number of rooks in the 5 by 5 board is not less than 1. If the number of rooks is not less than 6 on a 5 by 5 board, then we can always select 2 different columns so that one of the columns has at least 2 rooks and another column has at least 1 rook. And from these 2 columns, 2 rooks can be selected diagonally as shown on this diagram. Let us prove the case with 21 rooks placed in one 5 by 5 board. Such board has 4 empty squares. The algorithm of selecting 5 rooks that do not attack each other is as follows. Select the first rook so that its row and its column combined contain at least 1 empty square. Obviously, it's possible to do. The total number of squares in the row and the column that contain the selected rook is 9. So the maximum number of rooks placed in this row and this column is 8. If we subtract 8 from 21, we will get 13 rooks. This is the minimal number of rooks placed in the remaining 4 by 4 board. Then we should select one of 2 diagonal pairs of 2 by 2 boards, which contains more rooks than the other. Since the total number of rooks in 4 2 by 2 boards is at least 13, then the selected diagonal pair of boards contains at least 7 rooks. So 2 2 by 2 boards must have 4 and 3 rooks respectively. From that, we can select 2 rooks from one 2 by 2 board and 2 rooks from the other one, so that they don't attack each other. Thus, the total number of selected rooks is 4 plus 1, that is 5 selected rooks. To prove that it's possible to select at least 4 rooks that do not attack each other from 16 rooks or more, It suffices to prove that it's possible when exactly 16 rooks are placed in a 5 by 5 board. To prove it for 16 rooks, we can observe that 9 empty squares are among 25 squares. 25 minus 16 is 9. That allows us to select the first rook so that its row and its column combined contain at least 2 empty squares. Then the total number of rooks placed in the remaining 4 by 4 board is at least 16 minus 7 equal 9 rooks. Then the total number of rooks in one of the two sets of 2 by 2 boards is not less than 5. That results in either 4 and 1 rooks respectively in two diagonal 2 by 2 boards, or 3 and 2. In either case, you can select 2 rooks that do not attack each other from one 2 by 2 board and 1 rook from the other. That gives us 2 plus 1 and plus 1 equals 4 selected rooks. Finally, we need to prove that at least 3 rooks that do not attack each other can be selected from 11 or more rooks placed on a 5 by 5 board. It suffices to prove it for exactly 11 rooks on the board. Such board contains 14 empty squares. This allows us to select the first rook so that its row and its column combined contain at least 3 empty squares. Then the remaining 4 by 4 board, after exclusion of that row and that column that contain the selected rook, contains at least 11 minus 6 equals 5 rooks. Then the selected set of two diagonal 2 by 2 boards that has more rooks than the other must have at least 3 rooks. That results in 3 rooks in one 2 by 2 board and no rooks in the other, or 2 in one and 1 in the other. In either case, we can select total 2 rooks from these two 2 by 2 boards. That gives us 2 plus 1, 3 selected rooks. We're done.